Hi, Algebra 2 students. We are going to talk a little bit more about Lesson 57, exponential growth and decay. My book is a little bit different than yours, especially on this lesson. So if I go a little bit off course from what your book talks about, just bear with me, please, and thank you. First thing that we're going to talk about is basically what is exponential growth. If you think about it, an exponential function is anything that has an exponent in it. So anything that has something that might look like y to the x. Or maybe you have a function f of x equals something with a constant and another constant raised to the x power. Anything that looks like this is going to be called an exponential function, mostly because it has this nifty little exponent right there. Exponential function. One of the places where we use exponential functions a lot is in the calculation of interest, whether it's interest you owe or interest that the bank or whatever owes you. And if you think about it with me, and you have maybe $1,000, and the bank is going to pay you interest on that, maybe $1,000 at, we'll say that you've got a very generous bank and they're going to pay you a 5% interest yearly. And you wanted to figure out how much money you would have at the end of a year. You would take that $1,000 and then you would multiply it by that 5% or 0.05 over 12, because they're paying 5% in a year, not every single month. So at the end of 1 month, you would have this much interest, and then you would add $1,000 to it, right? And if you think about it, you could write that another way, because you could factor out that $1,000, and you would say that you have 1,000 times I'm rewriting in a different order, 0.05 divided by 12 plus 1, right? Well, that's pretty cool, but that would be only after 1 month. So if I wanted to find the interest that I would have after 2 months, I would take this total and I would multiply it again by that 0.05 over 12 and then add to it the amount that I had. So basically I would be taking this whole number and I would be multiplying the 1,000 times the 0.05 over 12 plus 1. That's how much I have after 1 month. And now I'm going to be multiplying again times the 0.05 over 12. And that would again be the amount of interest that I have. So I'd have to multiply it or add to that the amount of money that I had when the month started, which is this amount up here in that line. This looks kind of yucky, doesn't it? And then I could factor out what's common, which is this bit right here. And I'm going to have a 1,000 times 0.05 over 12 plus 1. And then I'm going to have a 0.05 over 12 plus 1, because when I factor this whole thing out here, that's what's going to be in this circle. I have a plus 1 left over. And this is going to be the total after 2 months, right? So that's the total after 2 months. Well, after 3 months, I'm just going to be adding or multiplying this whole thing by the stuff that's inside the brackets again. And after 4 months, I'm going to be multiplying that whole thing by the stuff that's inside the brackets again. So really, a shortcut way of figuring that out would be to be multiplying the 1,000 times the 0.05 over 12 plus 1 to the n number of months that I'm going to actually have it. And if I wanted to do that for a whole year, I would put my 0.05 divided by 12 plus 1, all of that to the n power, and then multiply that answer times 1,000, and I would have my total balance after 12 months of getting that interest rate. So this is kind of how we figured out the problem that we've talked about in class already. How you use it is exactly how you've already been using it. Like on problem B, on page 409, where you have a savings account that earns an annual rate of 3.5% interest, compounded continuously. So this is a different problem than the one that we actually just talked about. If the account begins with an principal amount of $5,000, the principal is $5,000, what will its value be after 4 years? 4 years. So the problem that we just did prior to this was when we had it compounded every month. This was compounded monthly. So that meant that we were going to be dividing our interest rate by 12 and then using n as the total number of months. But now they're saying compounded continuously, which means that the equation changes just a little bit. If it's compounded continuously, then instead of using an interest rate inside the parentheses like we were just doing, what we're going to do is have a new formula with a base of E, or Euler's number. So it's going to be our principal amount times E to the number of years that you want to do this, and then times the interest rate. So the number of years here would be 4. I'm going to put it n as the number of years, and interest rate is going to be I. So for us it would be 5,000 times E to the 4 times 0.035. And if you plug that into your calculator, the answer should be $5,751.37. Okay? So you only use E when you have continuous interest, continuous compounding. Okay, so that's a little bit different than something you may have seen before. However, when we have a different kind of problem where we have something that is half-life, we're going to use something that looks a lot like that. The exponential function, again, a general exponential function is going to be f of x equals any constant, whatever you want to use, b to the t, or to the x, because this x has to show up there. If we're doing time instead of like a distance or something, it will often be an f of t, but it will look the same because it's still an exponential function. What a half-life means is that it's almost always used with radioactive stuff. So I've got a beaker full of stuff, and it's radioactive, so it's glowing, right? We've got all of our stuff in there. And the half-life tells us the length of time it takes for half of this stuff to turn into something that is no longer radioactive. It's the amount of time it takes for this to decompose into something that is hopefully more safe than what the radioactive stuff is. So our half-life is going to be the time it takes for that stuff to be exactly half. See, I had 1, 2, 3, 4, 5, 6, 7, 8 little lines here, so now we're going to have just 4 because we've got half as much stuff in it, right? Okay, so how do we use this for a half-life problem? Well, in my book, I have a problem where it says a mass of carbon-14 atoms decays in such a way that half disappear every 5,730 years. And then it says what portion of the original mass remains after 8,600 years. So they don't really give you much in terms of how much mass was here to start with, do they? So what you want to think about is, well, if this was 100 grams, the half-life, in our case, 5,730 years, when that time is gone, if this was 100 grams to start with, it's going to be 50 grams when that period of time is over with. So how do I set this up and how do I figure it out? Well, let's think about it a little bit more. I know that if I have a function of time where it's 5,730 years, that's going to be exactly 1/2 of the value when time is 0, right? Because the answer I get here will be exactly half of what I started with. When time is 0, that's the value of the function when I'm starting. So this is another way to think about it. So if we think about it in terms of our exponential function, we know that b to the 5,730 power is going to be 1/2 of b to the 0 power. Remember, when we're starting, our time is 0. Okay, so if that's the case, do I know what anything to the 0 power is? Sure do. I know that anything to the 0 power is just 1. So b to the 5,730 has to equal 1/2. So how do we solve that? Well, we have to figure out what b is. And in order to do that, we're going to, well, we would have to take the 5,730th square or root of, oh, sorry. So b would be the 5,730th root of 1/2, which is kind of an interesting way to do it. I'm going to just pull up my on-screen calculator, which you can't see here, and actually, which has been disabled on this computer, so never mind, I can't do that. And my other calculator has been missing for a few days, so I can't get that for you either. But if you take that root of 1/2 on your calculator, you will get what b is. And then you can use that number, which, according to my book, b is going to be 0.99988. Do not round these numbers. You need several decimal places in order to get them to come out properly. Now we're going to find f of 8,600 to find how much is left after 8,600 years. So now we have 0.99988, and we're going to put 8,600 in there, and that means that we will have approximately 0.3563, or about 36% of it will be remaining after 8,600 years. That's basically how you're going to go about doing these sorts of problems. Okay. We'll do more examples in class, but I do want to do letter C in my book, which says a mass of carbon-14 atoms decays in such a way that half disappear every 5,700 or 5,730 years. What portion of a 10-kilogram mass of atoms will remain after 9,000 years? So we know that our equation is going to be f of t equals b to the t power. And I know that f of 5,730 is going to be 1/2 of f of 0, because this is the length of the half-life, right? What portion of a 10-kilogram mass will remain after 9,000 years? Well, we can use our same thing that we were just doing. We can say that b to the 5,730 equals 1/2 of b to the 0, which is going to be 1. So b is going to end up being exactly the same number that we figured out before, because we already figured out what the half-life of that is. So now, in order to figure out what b of 9,000 is, we have to do our substitution, and we should get an answer of about 3.4 of about 3. this is going to be about 0.34. And if we multiply that by our 10 kilograms, remember this is going to, or 34%, if we multiply that by our 10 kilograms, we will get 3.4 kilograms that are actually left after the half-life, or after the 9,000 years has expired. Okay? I hope that makes some of the homework a little easier to understand. If not, we will talk about it in class. This is just one chapter that where my book discusses it very, very, very differently than your book does. So please bear with me as we go through those. Completing the square is lesson 58. I also want to talk about completing the square very quickly. Completing the square is another way that we can learn to factor using some of the tricks that we've already been talking about. So, for example, there's one in my book that says, let's solve this one. This quadratic equation is x squared minus 10x plus 25 equals 9. And if I can solve this with factoring, that's often the easiest way to solve it. So usually I would have to move this 9 to the other side of the equation and then factor the normal way that we've been taught to factor. But let's see if we can factor this without moving that 9 over. In order to do that, I want to try to factor the left-hand side all by itself, because when I looked at that, it just seemed like, you know, I think that left-hand side already factors. And if I'm careful, I know I want to find numbers that multiply to 25 and add to negative 10. And I know 5 times 5 multiplies to 25, but that adds to a 10. So I can try a negative 5 times a negative 5, and that adds to a negative 10. So that's what I'm going to have. X minus 5 times x minus 5 equals 9, which is going to be x minus 5, quantity squared, equals 9. X minus 5, if I take the square root of both sides, equals plus or minus 3, and x equals 5 plus or minus 3. So 5 plus 3 is 8, and 5 minus 3 is 2. Those are the two answers that I could get. Okay. This is pretty close to completing the square. But notice what we did here. What the important thing that we actually did is that we noticed right away that this was a perfect square, quadratic, right? And if I factored this out, the left-hand side, I was going to get an x minus 5 times itself. And then I could take the square root of both sides. And if I could use this fact somehow, somewhere else, then maybe that would solve some other problems for me as well. So this whole completing the square idea, let's look at this idea. If we can see if we get it figured out. If we have x squared plus 18x, and we are going to want to factor this. Let's say it's equal to 0. How can we factor this using the completing the square method? I could factor out an x and then see what happens, but that's not going to help me as much. What I really want to do is complete the square. So how can I force this to be something where I have a perfect square here on the left-hand side? And the answer is that I can divide this term in front of the x. I can divide this coefficient by 2 and then square it. So what I'm going to have is an x squared plus 18x. 18 divided by 2 is 9. So I'm going to add a 9 squared. Because when I add a 9 squared, that makes this a perfect square, which is going to be an x plus 9 squared. Now try it. You FOIL this out and see if you get exactly that back. The trick is that since I have this equal to 0, I have to add that same number to both sides, right? So I added a 9 squared. I have to add 81 to the right side as well. It's equal to 81. And now I can take the square root of both sides, so that's going to be an x plus 9 equals a plus or minus 9. And I'm going to get x equals a negative 9 plus or minus 9, which is 0 or negative 18. Those are my two answers. One of the advantages of doing this with completing the square is that if I were to need to graph this for any reason, this is going to help me put it into that x minus h plus k notation that helps me to graph our quadratics. Okay, so that's one of the reasons that we would need to complete the square. Also, sometimes it's just easier to do some of this work by completing the square. Let's do another example, though. The example I want to do is x squared minus 14x minus 8 equals 0. And I know I'm going to need to factor this, so I would want to find something that adds to or multiplies to negative 8 and adds to a negative 14. Multiplies to a negative 8 and adds to a negative 14. It's just not coming to me. So I'm going to complete the square instead. So let's do it this way. X squared minus 14x. And since I'm going to be completing the square, I'm just going to move this number, the constant, over to the other side. And remember, when I move it to the other side, I move it to the dark side, so it's negative here. It becomes positive over there. When I do that, now I have to figure out what number can I put as the constant here, and that in order for me to complete the square. And that always has to be this term, this middle number, coefficient, divided by 2 and squared. So negative 14 divided by 2 is negative 7 squared. So plus a negative 7 squared. What is negative 7 squared? I sure hope you said that. So if this is the case, then I have x minus 7 squared equals 57, right? Now I can take the square root of both sides. And remember, when you do the square root, it's a plus or minus, and that's going to be a 7 plus or minus square root of 57. Okay? And that's how you complete the square. It's the tricky part is making sure that you look at that middle term, divide it by 2, and square it. Okay? Let's do another example if we can find one. I'm on letter A on page 417 on the lesson practice, where we have x squared minus 2x plus 1 equals 36. Can I factor this left-hand side? It is an x minus 1 squared when I factor it equals 36. Taking the square root of both sides leaves me with x minus 1 equals plus or minus 6, because 6 is the square root of 36. So x equals 1 plus or minus 6. So that would be 7 or a minus 5. Right? Okay, another example. X squared plus 16x plus 64 equals 6. Can I factor the left-hand side? X plus 8 squared equals 6. All I did on the left was factor it, so I don't have to change anything on the right. Now if I take the square root of both sides, I have x plus 8 equals square root of 6, and that's a plus or minus. So x equals negative 8 plus or minus the square root of 6. Okay, we weren't really completing the square there. We were just using our ability to factor this into a perfect square. Let's actually do something where we complete the square. How about x squared minus 20? And we're going to set that equal to 0. Sorry, x squared minus 20x. To figure out what we have to add to this left-hand side so that it becomes a perfect square, we're going to divide this by 2, which is negative 10. So plus negative 10 squared. What is negative 10 squared? 100. So the left-hand side now, we're going to look and see this is x minus 10 squared equals 100. This number is always going to be this number divided by 2, right? Always. So then we take the square root of both sides. X minus 10 equals plus or minus 10. Take the square root, remember? And x equals 10 plus or minus 10. If it's a plus, we'll get a 20. If it's a minus, we'll get a 0. Two answers, 20 and 0. Okay. Let's see. Let's do one more like that. We will do x squared plus 26x minus 2 equals 0. Okay. We could try to factor that. Two numbers that multiply to be a -2 and add to be a 26, but I don't really want to do that. How about you? Let's just complete the square because it's easier. Divide by 2, it's 13, so plus 13 squared. If I add 13 squared to the left, I've got to add it to the right. 13 squared is 169. So this becomes an x plus 13, and this becomes a 171. Square root of both sides, x plus 13 equals square root of 171, and x equals a -13 plus or minus square root of 171. And that is how you complete the square. Okay. Any questions? I guess we'll talk about them in class. I hope you had a great weekend, and we will talk again in class. Good night.